There's a few loose ends from section 1.3 that I want to finish up here, and I am going back to old school of just using a pen and a piece of paper to write on. Typically, I try not to use the paper because it just goes in the recycling bin, and if I could just do it electronically, then I don't have to worry about throwing the paper away. But anyway, until the new pen comes in, I'm going to do paper and pencil here. So there's a couple of things, a few definitions. Let's sort of work backwards from the way the book does. There is the notion of the trace of a matrix. The trace of a matrix. So if I have, it's only for a square matrix. A is a square matrix, so n by n matrix. Then we have that the trace of A is the sum of the entries on the main diagonal. So A11 plus A22 plus all the way up to ANN. For example, if I had the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, then the trace is 1 plus 5 plus 9, which is 15. Okay. There's also the notion of the transpose of the matrix. So transpose of A. And this is where the rows and the columns are reversed. So, or reversed, are interchanged. I should choose the word interchanged instead. Now, symbolically, I might say that Aij, and here's the notation, they use it kind of like an exponent, transpose, is equal to the matrix Aj. So what we've done is we've interchanged all the rows and columns. So looking at this from the point of view of, let's say 1, 2, 3, 4, 5, 6, transpose that matrix, every row becomes a column and every column becomes a row. So the first row becomes the first column, the second row becomes the second column. So that's what we mean by the transpose of a matrix. Okay. Now, there's one more definition that is kind of fundamental to a lot of the stuff that we do. So if there's a definition that you want to learn, well, of course you want to learn all of them, but let's make sure we know what the next one is here. So the next definition I want to throw out here to you is the notion of linear combination. Now, in this textbook that we're using, they give the definition of linear combination in a couple of different places. I just want to give one and let it include everything. So, if A1, A2, up to AN is a collection of things, or a set of things. Now those things might be variables, that might be functions, they might be matrices. I don't really care what they are. Then the following is what we want. Then let's do this. C1, A1 plus C2, A2 plus up to Cn, An is a linear combination of the AIs of A1 up to AN with coefficients C1 up to Cn. So I say I don't care what these things are. I mean, to some extent, it needs to make sense to be able to multiply any one of these by a number, and then add them all up. So we will be taking linear combination of matrices, we'll be taking linear combinations of variables, we'll be taking linear combinations of functions, of vectors. I mean, there's a lot of things that we'll do throughout this quarter where we take linear combinations. And so this is something I really want you to know what the definition is. A linear combination, a shorthand way that I have of saying it is it's a sum of multiples. So you got a bunch of things, you take multiples of those things and you add them all up. So a linear combination of the AIs is a sum of multiples of AIs. So they talk about it here because they notice that in talking about matrix multiplication, if you, let's do a fairly simple one here. Let's do 1, 2, 3, 4, 5, 6 times. I just want to do a column matrix here. Let's do 2, 4, 6. Right? That really what happens, right? The way we defined it looked like this. This would be 2 times 1 plus 2 times 2. Plus 2 times 1 plus 4 times 2 plus 3 times 6, and then this would be 2 times 4 plus 5 times 4 plus 6 times 6. It's that matrix, which I know that I can think of this, I don't usually do this, but I can think of this as the sum of 3 matrices, 2 times 1, 2 times 4, plus 4 times 2, 4 times 5, plus 6 times 3, 6 times 6. And then I notice, oh, but look, this thing right here is just 2 times the matrix 1, 4, plus 4 times the matrix 2, 5. Whoops, there's no fraction bar there. 2, 5. And then 6 times the column matrix here, 3, 6. And so what the book points out is that matrix multiplication, when you're multiplying by a column matrix here, is really just a linear combination of the columns of this matrix here. I got the column 1, 4. It's being multiplied by 2. I've got the column 2, 5. It's being multiplied by 4. I got 3, 6. It's right here being multiplied by 6. So I have a linear combination of the columns of this matrix where the coefficients come from the rows of the second matrix, right? The entries in the second matrix. And they have a theorem that states something to that nature. Part of it is just trying to visualize how this is being done. Also, at that point, they're leading up to something we talked about in the last video of our systems being linear combinations as well. That you have your coefficient matrix and your variable matrix. We ended up the last video talking about if you have a system, 2x plus 4y equals 7, x minus 3y equals 5, that we turned that into 2, 4, 1, negative 3 times xy equals 7, 5. So over here, this product, the columns are being multiplied by, well, the first column is multiplied by x, the second column is multiplied by y, and you have a linear combination of those columns. There's a lot of different ways of thinking of these things. We're trying to point out a bunch of them now. Gives you different options. As we do different things this quarter, the more options you have as to how to think of things, probably the better off you are, the more likely you're able to find solutions to problems or proofs to theorems. So anyway, try a bunch of problems here from section 1.3. We will we will do some in class on Monday. We'll probably look at some 1.2 stuff as well, because we didn't do that today. So anyway, have a great weekend.